Hello, everybody. So this is section 2.3 in your Calculus 3 class, OpenStax book. And the topic of the section is the dot product. It's one of the nicest things that you will learn. It's very simple and easy, and it is incredibly useful. Okay, so I hope you like it. And then throughout the next weeks and months, you would really appreciate the usefulness and the simplicity of the dot product. So here you go. Okay, so the section 2.3, the dot product, and this works in basically any dimension, 2, 3, 4, or any sort of n-dimensional vector space. All right, so I'll first give you the definition of this. All right, and again, some of you may have seen this already. In R2, I'm going to give you the two-dimensional vector, two vectors first. Let U be, let's say, A1, B1, and V be A2, B2, okay? Simple enough, all right? Then the dot product, and we use this dot because it is the dot product. The dot product of U and V is simply A1, A2 plus B1, B2. Now, how much simpler can you get, right? Because all you are doing is adding the X coordinates together and the Y coordinates together, all right? Now, similarly, in R3, if you have A1, B1, C1 dotted with A2, B2, C2, then the dot product is A1, A2 plus B1, B2 plus C1, C2. So it's really the sum of the products of the respective or corresponding coordinates, all right? And so that's very simple. And what can you do with something so simple? All right. So first of all, let me just say something else here too. U dot V is, as you can see, and you, by the way, you see that I am not multiplying two vectors, right? So I am not defining a product of two vectors. In fact, there is no such thing as the standard multiplication or product of two vectors, but we will have the dot product here, and in the next section we will learn what is known as the cross product of three-dimensional vector space vectors. But you can see U dot V is not a vector. What is that then? What kind of an animal is this? Well, you can see this is a real number, okay? So it's in our the set of real numbers. All right, let me give you some examples, all right? And it's not like you really need a lot of examples because it's so easy to calculate. Here, let me just do a little bit of a drawing. Okay, so 2, 3, what kind of a vector is 2, 3? Oh, I have a nice, cool way of drawing these vectors. 2, 3 goes from 0, 0 to 2, 3. Right, that's the vector 2, 3. 1, negative 2 would be something like that, okay? And then negative 4, negative 2, I guess I can do that, all right? So I have three vectors here, all right? So the first one, okay, go back. Okay. So U is 2, 3. My V is 1, negative 2. And my W is negative 4, negative 2. Okay. And so maybe you can pause and try to figure out the dot product of two of these things. Like for instance, what's U dot V? Okay. Now it's very easy for you to calculate U dot V, right? Because all you have to do is to multiply the two X coordinates together. That's 2 times 1 plus 3 times negative 2. Okay. So that's 2 minus 6. And the answer is negative 4. It's telling you something, okay? Now, what is it telling you? Well, the fact that it's negative is telling me something, and soon it'll be telling you something, okay? How about V dot W? What's V dot W? Well, that would be 1 times negative 4 plus negative 2 times negative 2. And that's negative 4 times negative 4 plus positive 4, okay? And that turns out to be 0. Now, when the dot product is 0, it is very important. It's telling me something extremely important here. And by the way, I think you can agree. In general, u dot v has to be equal to v dot u. Why is that? Well, because you have this multiplication and addition, both of which are operations which we call are commutative. Yes, right. Also, let's do a u dot u. Okay, so what is u dot u? Well, that's 2 square plus 3 square, right? Because u is just 2 dot 3. So when you do that, of course, it's 9 plus 4, or 4 plus 9, that's 13, okay? And you may, well, should I tell you this yet? Yeah, okay, notice here, if you have to find the norm of u, remember from an earlier section, what you do is you take the square root of x squared plus y squared. And that's exactly the square root of the dot product. Okay, so it is easy to see from these two calculations. I mean, I know this is just an example, but it's easy to generalize that for any vector u, the norm or the modulus or the length of a vector is simply the dot product. I mean, the square root of the dot product of u with itself. Okay, and in fact, in some abstract vector spaces, we use this as the definition for the length of a vector, because sometimes you may not be able to see a vector in higher dimensions. All right, I'm going to go ahead and start writing some properties. Now, these properties are actually theorems that are easy to prove. I'm not going to prove these. Many times the proofs are pretty obvious for these, but properties of the dot product. There are so many things I want to tell you. So I'll try to restrain myself, but I will tell you this one thing. We call this in the most English-speaking countries, the dot product, okay? For a very good reason, because we use the dot, okay? But we tend to be very informal in our mathematical language, especially in the Western world or in the English-speaking world. The rest of the world does not call this the dot product, even though they use the dot also, okay? So more technical name for this, and we will generalize this later, hopefully. Oh, no, not in this class. In linear algebra, math 214, we will have a generalized version of this. And a dot product is one of these products called an inner product, okay? There are many types of inner product, and this one happens to be called, after a great mathematician, Euclid, Euclidean inner product. Okay, so when if you read a book, especially from foreign language or something, when the book refers to the Euclidean inner product, that's what we in America call the dot product. Okay, and the dot product is very simple, as you see here, and it has many nice properties. Okay, so for instance, I already mentioned this, but u dot v is exactly the same as v dot u, and that's what we call the commutative property. And again, I mean, the thing is, if you have to rigorously prove this, you just use the definition, but it's very easy to see how you would prove something like this. Number two, and again, you can go ahead and do this calculation on your own using the definition, but if you have u plus a dot, parentheses v plus w, then it turns out you can easily apply, what should we call this? Yeah, the distributive property. And so u dot v plus w turns out to be u dot v plus u dot w, and it is called the distributive. In other words, you can basically do what we call the FOIL, the first, inside, outside, and the last, because of this property here. Now, if you have a constant times u dot v, you can imagine this constant can be considered the scalar for the first one. So cu, oops, yeah, dot v, one way to write that. Or it turns out you can also write this as, and this is taking some time again, right? It could be written as u dot cv. Okay, that's also a possibility. And then I have a couple more things here. Okay, I had to pause my monitor for the computer for a moment, but I will pick it up where I just left it. So the third property I mentioned was that the scalar can just kind of move in and out, of this. There's a C here, and there's a C here, there's a C here, and of course C is a scalar, which is an element of the reals. All right, and then fourth one, the fourth property here, this is easy. What's zero? Oh, I'm sorry. This should be a zero vector dot v. That is the number zero, right? Now notice here, I don't put this arrow on top of it because that's not a vector. So it is a number zero, the number zero. And then finally, as I mentioned, v dot v is always going to give you the norm of the vector squared. And in fact, you can tell that the v dot v is always zero. I mean, always, what did I say? Always positive, okay? Well, almost. There's one situation where v dot v is equal to zero, and that is IFF. You okay with this? If and only if and only if v is the zero vector, okay? And you can see that that's the only time it happens. All right, so this leads us to something very, very powerful. Okay, so I needed to tell you these properties because I needed to show you something incredible about the dot product. Okay, so I'm going to first draw this picture of a, and it doesn't have to be these two vectors, but I'm going to go ahead and draw these two vectors that meet at the angle theta. Okay. Now, of course, the picture will be slightly different if the angle theta is obtuse or right angle, but it turns out it's still true in general. Okay, so I have u and v meeting like this. Right. Remember what u minus v was? U minus v is this vector that goes from, I'm going to draw this in a different color. Okay. The different color, meaning that would be a nice color. All right, so this is a vector going from the tip of v to u, okay? And I mean tip of v to tip of u. We called this vector previously u minus v, and it is what that is because u minus v plus v is going to give you u, as you can picture here. All right, now let's try to write the length of this vector u minus v, and you probably don't know where it's going right now, but that's okay. Try to write the norm of this v, u minus v squared, okay? So what is the square of the magnitude of the difference u minus v? Well, the property 5 tells you, remember what property 5 is telling you? Property 5 is telling you that the square of the length of any vector is the dot product of that with itself. All right, so this turns out to be u minus v, which is a vector, dotted with itself. Okay, and then we have the distributive property. All right, and if you repeatedly use the distributive property on this, you can actually do the FOIL just like you do in your algebra class. All right, so this turns out to be u dot u minus u dot v minus v dot u, and then minus negative. So it's going to be plus v dot v. Now notice here, I don't write v squared because there is no way to square a vector. Okay, so this is different. It's v dot v. All right, so what do you get? All right, you know this is the norm of v. Sorry, norm of u squared. And the last thing I wrote, v dot v, is simply the norm of v squared. And all we have left in the middle is the two identical terms. I know v dot u is the same as u dot v, so it's minus 2 twice the quantity u dot v. Okay, no problem here. What's a big deal? Okay, you will not see that yet. All right, but on the other hand, and I don't know if you remember this or not, you should. The law of cosines for any triangle. The law of cosines tells you how to find the third vector u minus v. In particular, it'll tell you how to find the square of that, the third side length in terms of the other two lengths, two sides, and the angle between them. You remember this? So that the third side of any triangle can be obtained by this formula. If you look at the law of cosines, typically you have the length of the third side as a square root of this big thing here. But this side is actually the norm of u squared, the first side squared, plus the second side squared, minus, you remember this, 2 times the first side times the second side times the cosine of the angle between them. Okay, let's go over this again. The law of sine says that the length of a third side of a triangle is always equal to the square root of, and I'm not writing the square root because I'm squaring both sides, but it's the square root of the first side squared plus the second side squared minus 2 times the first side times the second side times the cosine of the angle between them. Now, if theta happens to be the right angle, then cosine of that angle is 0. So this last term will disappear and you have the Pythagorean theorem, right? It says c squared is equal to a squared plus b squared. Now notice here, okay, I have written the same quantity, the third side squared, in 2 different ways. So these must be equal to each other. All right, this is an amazing thing. What did I just say? Okay, I'm going to rewrite this. Okay, this will tell you how exciting the dot product is. You probably notice that my voice is is sort of excited because I am. I can't wait to show you this. All right, so on the one side I have the norm of u squared plus the norm of v squared minus 2 times the dot product. That is equal to the norm of u squared plus the norm of v squared minus 2 the norm of u, the norm of v, cosine of theta, okay? Now, one of the nicest things about mathematics is when things cancel, because what seems to be so ugly can become something so beautiful, right? And so, I like to use different colors. U squared and v squared, they both appear on the same, in the same form in both sides. And -2 occurs in both of these, right? So you can eliminate that too. What turns out, what this is telling us is that the dot product is exactly the norm of the first times the norm of the second times the angle between them. Okay, now this turns out to be one of the most important formulas in this course. And I should say, and where is this? I'm trying to make my points, okay? So this is one of the most important things in vector calculus and consequently in this course, all right? So remember that the dot product can be easily obtained, easily calculated, and it also is equal to the length of the first vector times the length of the second vector times the cosine of the angle between them, all right? So that is what's very important, all right? Now, this always tells you something, and I'm going to stop at this point. Well, let's see, I'm going to tell you just a little bit more, and then I will stop this section of the video, and then I will go on to the next portion. All right, so hang on tight real quick here, all right? What is this telling us? This is also telling us this. Therefore, remember the 3 dots means therefore, cosine of theta, if you want to look for the angle between 2 vectors, all you have to do is to take the dot product and divide it by the product of these 2 vectors, okay? And as long as as long as neither of them is a 0 vector, you can find the cosine of the angle and then take the inverse cosine to find the angle between them. Of course, if one of them is 0, it doesn't matter, because if you have a 0 vector, the angle between 2 vectors is, well, it doesn't mean it's meaningless, okay? So, by the way, something else here, this is always positive, right? Now, again, I'm assuming that neither of them is a zero vector. So both of these are positive, and the product of two positive numbers is also positive. Okay, so therefore, because these are positive, here's the fact. Very important fact here. And in fact, I'm going to let you figure this out. Remember, the bottom is always positive. Okay, so that means that this side, cosine of theta, and this numerator, u dot v, have the same sign. If one of them is positive, the other is positive. If one is negative, the other is negative. Okay, so what do you think this means if the dot product is positive? And what do you think this means if the dot product is negative? Okay, and what do you think this means if the dot product of two vectors is equal to 0? Okay, I want you to figure this out. I think you can. These will tell you, each of these cases will tell you something about that angle theta. I hope you remember your trigonometry, especially about the cosine of an angle. And once you fill this out, you go to the second part of this video, and then we will get the rest of that going. All right. Unfortunately, because this section is rather long, I think we'll have 4 segments or 4 parts of the video, but that's okay. You want to learn the dot product well. So when you think you are done with this fact, complete the fact statements, then come back and I will give you the answer.